Good day everyone, we are from Group 10 Section 2 Communication Principle, and our team comprises of Lok Jia Hao, Loh Jien Seng, Loy Zhi Heng and Jia Yong. Today, we are thrilled to share with you the essential principle of telecommunication, amplitude modulation, angle modulation and radio-digital modulation. To begin, what exactly is a communication system? A communication system is a network of devices and technologies that transmit information using electrical signals, electromagnetic waves, or optical signals. These systems are the backbone of telecommunications, allowing us to send and receive data seamlessly, whether it's a phone call, an email, or a live-streamed video. Let's talk about the methods of data transmission, which are categorized into two main types: analog and digital. Analog transmission involves the continuous flow of signals, where data is represented using variations in amplitude or frequency over time. This is commonly used in traditional telecommunication systems, such as radio and TV broadcasting. On the other hand, digital transmission relies on discrete signals, typically represented in binary form as zeros and ones. This method is more reliable and widely used in modern communication systems like computers, mobile phones, and the internet. One of the key elements of communication systems is modulation. Modulation is the process of altering a carrier signal's properties, such as amplitude, frequency, or phase, to encode information. But why is modulation necessary? For one, it enables long-distance transmission by increasing the frequency of the carrier signal, making the antenna size practical. Modulation also helps reduce signal interference and improve transmission efficiency, making it an indispensable technique in modern communication. There are three methods being categorized under analog modulation, which are amplitude modulation, frequency modulation, and phase modulation. In amplitude modulation, the amplitude of carrier signal is varied according to the message signal, as shown in the diagram, AM output signal. The frequency and phase of carrier signal will remain constant. Whereas in frequency modulation, the frequency of the carrier wave is adjusted based on the input signal. For instance, based on the diagram, the frequency of modulated signal is the highest when the amplitude of message signal is at its peak value. And the lowest frequency in the modulated signal is located at the minimum amplitude of message signal. The range of frequency that modulated signal can have is called as maximum frequency deviation. Phase modulation is the process of altering the phase of the carrier wave according to the message signal. While the amplitude and frequency of the carrier wave remain constant, it is the phase that changes to encode the information being transmitted. Next will be digital modulation. In digital modulation, the carrier wave's properties are varied to represent binary data. One of the technique include amplitude shift keying, which is the change in amplitude to represent 1 or 0 as shown in the diagram. In frequency shift keying, we have one frequency assigned to binary 1 and another assigned to binary 0. The frequencies are shifted to denote binary states. Another technique in digital modulation is phase shift keying. The phase of the signal is varied accordance to the change of binary state for encoding data. There are two ways of phase shift keying, which are binary phase shift keying, BPSK, and quadrature phase shift keying, QPSK. Each methods can have different transmission speed, and we need a term to set the standard of transmission rate. Therefore, BU rate, or also known as symbol rate, is the number of symbol changes per second in communication system, where each symbol can represent one or more bits of information. Shift keying uses the BU rate to define the speed of symbol transitions in the communication system. Now, let's talk about binary phase shift keying, or BPSK, one of the simplest and most widely used digital modulation techniques. BPSK uses two distinct phase states, typical 0 degrees and 180 degrees, to encode the binary values 0 and 1. As seen in the diagram, the carrier wave shifts phase whenever the binary data transitions between 0 and 1. This clear distinction between states ensures accurate data recovery at the receiver end, even in challenging communication conditions. Quadrature phase shift keying, QPSK, is a digital modulation technique that improves upon binary phase shift keying by encoding 2 bits of data per symbol, effectively doubling the data rate compared to BPSK. QPSK uses 4 distinct phase states, typically 45 degrees, 135 degrees, 225 degrees, and 315 degrees, to represent 2 bits of binary data. For easier understanding of each phase state, we will use constellation diagram, which shows all possible symbol state as points, where their positions correspond to specific amplitudes and phases of the carrier signal. For example, the bit 00 will be producing a carrier signal with phase shift of 45 degree. Constellation diagram is like a map that helps you see how QPSK encodes and decodes data using phases of a carrier signal. Next, let's discuss quadrature amplitude modulation, or QAM, a powerful modulation technique that combines variations in both the amplitude and phase of the carrier wave to encode data. As shown in the diagram, each symbol represents a unique combination of amplitude and phase, which corresponds to a specific group of binary bits. In this case, 3 bits are represented by each symbol. This is why QAM is highly efficient in transmitting large amounts of data. Quadrature amplitude modulation, QAM, can have different formats, such as 8QAM, 16QAM, and 32QAM, depending on the number of bits each symbol represents. In this example, we see 8QAM, where each point on the constellation diagram represents 3 bits of data 000, 001, 010. The higher the QAM format, the more points there are in the diagram, which means more bits can be encoded per symbol. Let's now explore a significant recent advancement in modulation technology, 1024 QAM, developed by Samsung and Qualcomm. This innovation represents a leap forward in communication technology, increasing downlink speeds by over 20% compared to previous QAM formats. By encoding more bits per symbol, 1024 QAM achieves exceptionally high data rates. By implementing 1024 QAM, we have faster mobile connectivity, making it possible to handle large volumes of data seamlessly. It helps to support for bandwidth-intensive applications, such as high-resolution video streaming and virtual reality experiences, where speed and reliability are critical. While 1024 QAM technology is a significant advancement, there are a few misconceptions that need to be addressed. Some people believe that higher frequencies and complex modulation techniques cause health issues. This is not true. Regulatory bodies enforce strict guidelines for electromagnetic radiation exposure, ensuring public health is not compromised. Another common belief is that higher bandwidth technologies increase the risk of hacking. While higher data rates might create challenges in securing transmissions, these risks are mitigated with robust encryption standards and secure communication protocols. It's important to note that the modulation technique itself does not impact security. Let's also address the cultural misconception that new technologies are only for urban or elite populations. This is not the case. The efficiency of QAM, which enables higher data rates over limited bandwidth, allows high-speed communication to be extended to remote and underserved areas using fewer resources. These advancements ensure that modern communication technologies are accessible to a wider audience, bridging the digital divide and fostering inclusivity. That's all from us. I hope that you have learned something from this video. Thank you for watching.